study about cluster sampling. Actually, in simple random sampling, we select the units from the population which are elementary in type. But in many situations, this may not be possible in practice. For example, the list of households in a village or in a locality may be available to us, but the persons living in those houses may not be known in the listed file. So the cluster sampling is used in that situation. So here you see that a sampling procedure presupposes division of population into a finite number of distinct and identifiable units called sampling units. The smallest units in which population can be divided are called elements of the population and bunch of units, the clusters. When sampling unit is a cluster, procedure of sampling is called cluster sampling. So this application of this sampling is, as I told, that when a list of elements is not available, using a simple random sampling is not feasible. The method of cluster sampling is available in such cases. So thus, in a city, the list of households may be available, but the list of persons residing in the houses may not be available. Similarly, the list of farms are not available, but those of villages in districts prepared by census are available. So cluster sampling is therefore widely practiced in sample surveys. Now there are some assumptions. The assumption is that the population consists of n clusters of size m. That is, the population is finite, and we are selecting small n clusters from capital N clusters by simple random sampling without replacement. So here we denote by Yij. Yij, the value of jth unit in ith cluster. J goes from 1 to m. J denotes for the elementary units in a cluster, and I goes from 1 to n. This is for the clusters. So we first we define mean per element of ith cluster. Mean per element of ith cluster, that is yi bar, which is equal to 1 by m. Some j goes from 1 to m. Some j goes from 1 to m. Yij, the Yij, the mean per unit cluster. Now we define by y double dot bar. Y double dot bar, that is equal to 1 by n. Some j goes from 1 to n. Yi dot bar. So yi dot bar, you see, this is mean due to ith cluster, and so y double dot bar is the mean of cluster means. Y double dot bar is the mean of cluster means. And now we define grand mean y bar, which is sum of the elementary units. I goes from 1 to n, j goes from 1 to m, yij. So here some j goes from 1 to m, yij is the total of the values of elementary units in jth cluster, and summing all those totals, we write it by I goes from 1 to n, and dividing by nm, we get grand population mean. Now we can see that in case of equal size clusters, when the clusters are equal in size, then y bar will be equal to y double bar. Y bar will be equal to y double bar, because this value j goes from 1 to m, yij may be replaced by yi dot bar, the mean due to ith cluster. And its again total and sum will give you y double bar. Now we define mean square error between elements in ith cluster. Mean square error between elements in the ith cluster. So since there are capital M units in ith cluster and we are denoting yij, the jth unit in ith cluster, and yi dot bar is the mean due to ith cluster. So this si square, which is equal to 1 by m minus 1, and j goes from 1 to m, yij minus yi dot bar is square, will be mean square error due to ith cluster. Now we define by SW square the mean of the mean square errors, which is given by 1 by n, sum I goes from 1 to n, si square, the mean square error within clusters. And again we define a term SB square. SB square, the mean square between cluster means. There are capital N clusters, and those clusters have different mean, y1 dot bar, y2 dot bar, ym dot bar. So by this yi dot bar and reducing it by subtracting it by mean y bar, so this gives ysb square, 1 by n minus 1, I goes from 1 to n, yi dot bar minus y bar whole square, the mean square error between cluster means. So these two terms are very important, SW square and SB square. Here the notation SW, W denotes the mean square error within clusters, and here the B denotes the mean square error between clusters, cluster means. So these are the notations for population. Now we define similar notations for sample values. So as an estimator of y bar, consider mean of cluster means in the sample, namely y bar, y double bar is equal to 1 by n, I goes from 1 to n, yi dot bar. So this is just like we population value we have denoted here as y double bar is equal to 1 by n, some j goes from 1 to n, yi dot bar. And so y double bar is the mean of cluster means in population, and by replacing y values by small y, we get small y double bar is equal to 1 by n, some j goes from 1 to n, small y I dot bar. So this comes y double bar is equal to 1 by n, some I goes from 1 to n, yi double bar. So this is the mean of cluster means in sample. Now we have a result. The result is that the variance of mean of cluster means in sample, that is denoted by y double bar, is equal to 1 by small n minus 1 by capital N, SB square. SB square, just we have defined that this is sum of square between cluster means. So the theory statement or theorem is that if the clusters are selected by SRSWR, that is simple random sampling without replacement, the mean of cluster means in sample y double bar is an unbiased estimator of population mean y bar with variance v y double bar is equal to 1 by small n minus 1 by capital N, SV square. So the proof of this theorem is very easy if you remember the results of simple random sampling. So here you see the expected value of y double bar. You know y double bar can be written as 1 by small n, some I goes from 1 to n yi dot bar, and its expected value. So this becomes equal to 1 by n, some I goes from 1 to n, just repeated, and here expected value of yi dot bar. Now expected value of yi dot bar is obtained on the assumption that this value yi dot bar may take any of the values, capital Y1 dot bar, capital Y2 dot bar, capital Yn dot bar, which are population values, because we are taking the cluster randomly. We are taking a cluster, you say ith cluster, from capital N clusters. So this small yi dot bar, the mean due to ith cluster, may be any of the values y1 dot bar, y2 dot bar, yn, y capital dot bar in population. So the expected value of y double bar, which can be written like this, the expected value of yi dot bar can be written as 1 by n, some I goes from 1 to n yi dot bar. Now you know that if you are taking expectation, if x be a random variable, taking values x1, x2, xn, x1, x2, xn with probabilities p1, p2, pn, then expected value of x is equal to x1 into p1 plus x2 into p2 and so on plus xn into pn. So this is the definition of expectation, you know. In the present case, we have values, this yi dot bar assumes values y1 dot bar, y2 dot bar, and this yn dot bar with probabilities is equal to 1 by n, 1 by n, 1 by n. It is taking the values like this. So expected value of yi bar will be equal to y1 by n plus y2 by n, y2 dot bar by n, and so on, yn dot bar by n. This can be written as 1 by n, some I goes from 1 to n, yi dot bar, and which is exactly equal to capital Y bar we have already defined. So expected value of yi dot bar is equal to capital Y bar. If we substitute this value here, capital Y bar, and sum this small n times and divide by n, as we have done here, we get capital Y bar, the population mean. So we can say that sample mean Y bar is an unbiased estimator of population mean capital Y bar. This small y bar is an unbiased estimator of population mean capital Y bar we have proved. Now we are to find out variance of Y double bar. So for variance of Y double bar, we have by definition this expected value of Y double bar minus capital Y double bar. Capital Y double bar, that is the expected value of small y double bar. We have already discussed that capital Y double bar and this capital Y bar both are same in case of equal size clusters. So we are taking this value. Now this y double bar can be written as we have done 1 by small n, some I goes from 1 to small n, yi dot bar minus y double bar. Now we rearrange the terms like this: 1 by small n, some I goes from 1 to n, yi dot bar minus y double bar whole square. This 1 by n whole square can be written as 1 by n square, 1 by n square, and we make square of this value. We make square of this value. We make square of this value. So this square can be written into this form. You already know that we know that some ai whole square, I goes from 1 to n, can be written as sum of ai square, I goes from 1 to n, and plus sum over I, sum over j not equal to I, ai into aj. So we have already discussed in simple random sampling that this is true for n is equal to 2 or 3 or and so on, all the values of finite values of n. So we write this by putting ai is equal to yi dot bar minus capital capital Y bar, double bar. You can write this. ai is equal to small y dot bar minus y double bar. So this becomes equal to as ai square. This comes out to be some I goes yi dot bar minus y double bar whole square, and here yi dot bar minus y double bar, and here yj dot bar minus y double bar. And we can extend the expectation like this. Now expected value of yi dot bar minus y double bar whole square can be written as 1 by n, some I goes from 1 to n, yi dot bar minus y double bar whole square, as we discussed earlier. We write this term, we write this term by n minus 1 sb square, because we have already defined that sb square, which is sum of square between cluster means, is equal to this yi dot bar minus y double bar whole square. We have already defined sum of square between cluster means. So it can be written in this form. Now when we define expected value of yi dot bar minus y double bar minus this, so this term can be written as actually just we define expectation of a random variable. So expected value of, for getting expected value of yi bar, this out of capital N units, out of capital N units, you can write 1, 2, capital N, any, if suppose I is here. So if ith unit is selected out of capital N units, expected value of for expected value of this term, the probability of selecting ith unit is equal to 1 by capital N. Now in simple random sampling without replacement, where unit is selected and it is not replaced to the population, then when a unit is selected, the remaining units in the population becomes capital N minus 1. So out of those capital N minus this, out of those capital N minus 1 units, if jth unit is selected, probability of j becomes equal to 1 by N minus 1. So for expected value of this yi dot bar minus y double bar, yj dot bar minus y double bar, we write the values of small y dot bar, which is taking this yi dot bar minus double dot bar, and we write the sum I goes from 1 to n. Now and we write its probability as 1 by capital N. And for j we write the sum j not equal to I going from 1 to n, because the ith unit has already been selected from the population. So we assume that it cannot be equal to jth unit in the population, which is in the population itself. So probability of, we multiply it by probability of j, that is 1 by n minus 1. The whole result comes in this form. Now the summation is I goes from 1 to n, and here j not equal to I goes from 1 to n. So we rearrange the term in this way. We first put j is equal to I. So when j is equal to I, this term comes, you consider this one out. So here when j is equal to I, the term becomes yi dot bar minus y double bar whole square, as we are writing here. And the remaining term is taken minus subtracted. So for I goes from 1 to n, yi dot bar minus y double bar whole square. So this term can be written in this way. This now sum I goes from 1 to n yi dot bar minus y double bar. This becomes equal to sum I goes from 1 to n yi dot bar minus y double bar. This is equal to sum I goes from 1 to n yi dot bar minus n times y double bar. So this term is also equal to n times y double bar minus n y double bar, because we have already defined earlier that y double bar is equal to sum I goes from 1 to n yi dot bar by capital N. So multiplying this capital N by capital Y bar, this total can be written as n y double bar. The sum becomes equal to 0. So we are writing this value as 0, and here we substitute minus 2. So again this becomes equal to minus of sum I goes from 1 to n yi dot bar minus y double bar whole square, this divided by n into n minus 1. Now this term I goes from 1 to yi dot bar minus y double bar whole square by n minus. We are writing this by SB square. We are writing this by SB square. So this is SB square by capital N minus SB square by capital N. So expected value of this is equal to minus SB by capital N, and expected value of this first term is equal to this much. So here we are writing as n SB square by you write as n minus 1 SB square by n, minus this SB square by n, minus SB square by n, and multiply it by 1 by small n square. You find that this becomes equal to 1, this becomes equal to n minus 1. Okay. So we are to make further more sum. We have find out here a factor value of this term and x factor value of this term and x factor value of this term, and this term is being summed up to n times and n minus 1 times, j not equal to I going from 1 to n. So if we put this value as 1 by n square here, n minus 1 by n SB square, minus sum of this, this is SB square by n, and we make n minus 1, n minus 1 like this, and we are to sum this by n times. So this is equal to small n minus 1 by n SB square, here n minus 1 SB square by n. So solving this, this becomes equal to 1 by small n by this SB square. You can take small n out of the bracket and cancel it here, small n, and this n minus 1 by n, and here we can take capital N also out, and here n minus 1. So it becomes in this form. So this we are doing here as Vy double bar as 1 by small n minus 1, I goes from 1 to n minus 1 by n is b square, and this sum I goes from 1 to n, j not equal to I going from 1 to n minus s b square by n, and it solves in this form.